Hi everyone, and welcome to another seminar at Physics Latam. Today we have Pavel Mnev with a talk on 2D BF theory as a topological conformal field theory. Please remember to raise your hand at any point if you have any question, and now I leave you with Pavel. Please go ahead.
Thank you very much, and thanks very much for the invitation. I wanted to talk about two-dimensional BF theory, and with a particular gauge fixing. It turns out that it can be studied as a conformal field theory, and as a sort of nice kind of toy test case for various things conformal field theory, and moreover, it has a bit more structure than just a CFT. It's what's called a topological CFT, and even more structure. I'll talk about it. So then, as a basic case, I will talk about, and most of the time I will be talking about the abelian BF theory, and this is covered in this paper here. So the first link here, and both this is all work with Andrei Lossev and Donald Humans. And we wrote two papers about this story. So kind of the abelian part is covered in the first paper, and the non-abelian part is in the second paper. So now about BF theory. So it's a very interesting story in its own right, but in particular, two-dimensional BF theory. What is that? So, well, it's the following. Classically, it's the following model. So you fix some surface, two-dimensional surface, and you fix some Lie group, and little g would be its Lie algebra. So I want this Lie algebra to be unimodular. That means that traces of adjoint action of any group element are zero, and that follows, for instance, from the existence of a Haar measure on the group. So various examples of Lie algebras that you know, like semi-simple Lie algebras, are automatically unimodular. Some more exotic ones, like nilpotent, might fail to be unimodular. So and then the action of BF theory is the following. So it's the integral over the surface of B wedge the curvature of A. So, okay, and here let me also pair them. So I'll explain. So what are the fields involved? So the fields involved are A is a connection in a trivial principal bundle over sigma. Or in other words, I can identify connections in the trivial bundle with global one forms on the surface with coefficients in the algebra. So so that's the kind of the first field, A, and a connection one form, and B is just a function on the surface with coefficients in the dual of the Lie algebra. So then what is written here in the action is, well, I take the curvature of the connection. So this is a two form with values in the Lie algebra. Then I multiply it by this function. Actually, I don't even need the wedge sign, frankly, because it's just a function times a two form, which is a two form. But then I need to pair G star with G, which I denote by this canonical pairing. So this is a number valued two form, which I can integrate over a surface and get a number. So this is the action. So okay, and this is the name BF. So BF theory is just because of these two letters. So it's not for any two people starting with B and F. It's just for the two letters in the action. So now, okay. So in BF theory, by the way, you can formulate it in any dimension, essentially in the same way, but the field B will be a form of certain appropriate degree. But let's focus on the dimension 2. So the equations of motion in this model, very easy to figure out. They just tell you that A should be a flat connection. And so the curvature of A should be 0. And second equation is that the covariant derivative of B should be 0. So yeah, so B should be a covariantly constant function. There are also, it's also a gauge theory, so there are gauge transformations. So by the way, you see all right what I'm writing, right?
Yes, it's clear.
Does it need to be a Riemann surface? Do you mean that does it need to have a complex structure? No. So here there's no need to have a complex structure. So here there are no kind of geometric structures involved at all, except for, well, let's say orientation. Orientation is the only geometric structure used so far. We will need extra geometric structures later on, but so far nothing. So it's a topological theory in the Schwarz sense. So no geometric structures used. So now gauge transformations. So A is transformed by sort of a fiber-wise rotation in the principal bundle. Sigma has to be compact. Well, yes. Well, you know, yes and no. I mean, you can study it also on non-compact surfaces. You can study on surfaces with boundary, without boundary. I didn't want to say anything more specific about the surface here. We will spend a lot of today talking about sigma being the complex plane. So, I really don't want to insist on compactness. So now the gauge transformations are, well, the usual sort of action of fiber-wise rotations of the principal bundle. So, for instance, the connection one form transforms like that with G a little g group valued function on the surface, and B transforms just by conjugation. So, well, this is kind of a schematic way of denoting the coadjoint action on the dual of the Lie algebra. So, so this is the two-dimensional BF theory, and it comes as a certain degeneration of another very well-known model, which is called two-dimensional Young-Mills. So, of course, Young-Mills kind of took its started its life as a four-dimensional theory, but it turned out that it's interesting to study in other dimensions. In particular, in two dimensions, it's sort of almost topological theory, and in this limit that's relevant here, it becomes actually topological. So, two-dimensional Young-Mills theory, so written in the first-order formalism. So written in the first order formalism is given by the following action. So it's the integral over the surface of, well, B paired with the curvature of A plus, okay, the kind of square of B, no, should I denote it? Pairing of B with B times the area form on the surface. So, so these brackets denote the killing form, or the inverse of the killing form that's on the dual of the Lie algebra. So yeah, so two-dimensional Young-Mills doesn't really depend on the metric, but it depends on the total area of the surface. And for the area form, you can choose the sort of the Riemannian volume form. So various quantum answers into the Young-Mills depend on the area of the surface. But BF theory is the limit of area going to 0, or taking the area form to 0. So if I take the area form to 0, then this sort of second term vanishes, and what we recover is the BF action. And yes, so by the way, so how to recover the Young-Mills in second order formalism is just by integrating out the B field, which would result in something like well, the square of the curvature. Well, essentially this action with some coefficient which is like well, dependent on the normalization of the area form. So, okay, this is just a reminder of how to connect it to the Young-Mills, maybe in the form that looks more familiar. So actually, I should write the form here. So, okay, now I wanted to go back to the BF theory and moreover to specialize to the abelian case. So later on, we'll talk a little bit in the end about non-abelian given time. So, so I want to specify the Lie algebra to be reals. Also, let me denote the BF action that we had before as 0, because, well, we'll need to deform it in a certain way or do something to it. So in this case, the action of BF theory is just integral of BdA. And the fields are just, well, a 1 form with coefficients in reals and a 0 form or a function also with coefficients in reals. So very nice looking action. So, and well, the gauge symmetry is just shifting A by exact 1 forms and not doing anything to B. Now, I wanted to study, okay, so this is a gauge theory. So I want to study it with a particular gauge fixing. And the gauge fixing I'm interested in is, well, a very classical one, the Lorentz gauge. So the codifferential of A is 0. So now, so I see that there are some things in the chat. What's the difference between Y and Y star? Oh, that was G. Sorry, G. The G was the Lie algebra. So the algebra and its dual. So okay, now my gauge fixing is D star of A equals 0. So D star is the codifferential, so it's negative star D star. So where star is the Hodge star associated to some choice of metric on the surface. So okay, so this is the Lorentz gauge. And now I want to invoke something from the story of gauge theories, namely the Fadeev-Popov mechanism. So Fadeev-Popov mechanism, well, it's kind of says how to impose a gauge on a field theory, and essentially applying Fadeev-Popov mechanism in this example tells you that you should replace the action that we had with a new action, which depends on some extra fields. And the extra fields are, so, okay, so it's the old action plus some two extra things. So one extra thing is the Lagrange multiplier, which is a new field. Lagrange multiplier times the gauge fixing condition, which is D star A. But let me actually rather equivalently, I can write my gauge fixing condition as D of star of A vanishes. So let me write this gauge fixing term in this way. So the Lagrange multiplier is a new field. So you can imagine. Yes,
can
please?
I ask a question?
Yes, please.
Yes, so under this gauge transformation, S naught transforms exactly as S naught, or it transforms up to a total derivative?
Actually, not up to a total derivative. So yeah, the Lagrangian is, yeah, there is no total derivative term for gauge transformations.
Okay, thank you.
Yes, in some other examples like Chern-Simons, there are total derivative terms, but here no. So okay, so I see the question: is 2D Young-Mills exactly solvable? It is, and it is a very well-known story, but it's not what I'm talking about today. If you want to read about it, then there are famous lecture notes from the 90s on the archive by Kords, Moore, and Rangulam, which explains how this works. So, but yes, it is exactly solvable. And there's a very beautiful exact answer for 2D Young-Mills. So for the partition function on the surface. Okay, now let me, but I didn't want to tell kind of a standard story. I wanted to tell something less standard. So, okay, now the third term that we wanted to add here is, well, it's related to, well, geometrically to somehow the way that the gauge orbits, the angles between the gauge orbits and the sort of gauge fixing surface in the space of fields. And it's related to so-called Fadeev-Popov determinant, and it's kind of an integral formula for the Fadeev-Popov determinant. So the term that I'm adding here is B d star d c. So where little b and little c are two new fields, which are called Fadeev-Popov ghosts. So they are odd scalars, so anti-commuting or Grassmann variables, and they are scalar fields. So Lagrange multiplier is an even scalar. So B and C are, so it's one notational convention for them, and another notational convention, which is actually from the original Fadeev-Popov paper, was C and C bar. But little b is a notation more used in string theory. Let me use that one. So these are two new fields, which are odd scalars, and one can also prescribe certain z grading to them, and then C will be of grading +1 and B of grading -1. And this grading is called the ghost number. So, okay. Now, the space of fields, kind of the new space of fields, is the old space of fields plus all the new variables. So, the space of fields is, we have 1 forms on the surface for the field A. We have 0 forms on the surface for field B. We have also 0 forms for the field lambda, which is the Lagrange multiplier. We also have 2 copies of 0 forms, but sort of placed in degree -1 and in degree +1 with respect to this extra grading, the ghost number. And this is where the ghosts live, the B ghost and the C ghost. So this is the
Sorry,
space
this
of fields.
lambda, B, and C both are Lie algebra valued, right?
Well, the algebra is now just reals. I specialized to
Oh, these are
abelian
abelian. I
theory.
see, I see.
Yes, it's
Yeah.
abelian, yes. Later on, we'll talk maybe a little bit about the non-abelian case, but for now, let's talk about abelian BF. So, right. So now, this Fadeev-Popov mechanism, so replacing the action with this new action. And by the way, the point is that in Fadeev-Popov mechanism is a replacement of the path integral over fields modulo, classical fields modulo gauge transformations. So it is getting replaced by an integral over this entire collection of fields, A, B, lambda, little b, little c, but of the exponential of this new action. So somehow integrating over a quotient is kind of problematic for path integrals. So Fadeev-Popov mechanism is a sort of homological resolution in appropriate sense, or in the sense which was understood after Fadeev-Popov original work. So it's a replacement of that. It's a resolution of this original path integral over a quotient by a new integral over a certain supermanifold of fields. And this is this supermanifold of fields. So, okay, but now there's another kind of language for this new action, and this is the language of BRST formalism, so Becky, Ruhr, Starra, and Tutin. And so a key object there is so-called BRST operator, which is a differential on the functions on the space of fields. Or in another terminology, it's a homological vector field on the space of fields. But how does it work? So in particular, it's some operator that squares to 0. So this operator takes A2 DC And the reason that it takes A to DC is ultimately because the gauge transformation for A infinitesimal gauge transformation was that it was shifting A by an exact form, by D of some generator. And now this generator is promoted to a goes to a Grassmann field. Then in the abelian theory, B doesn't get any gauge transformation, so B is sent to 0. And then, okay, so for the extra fields that you adjoined when going to Faddeev-Popov formalism, so the ghost B is sent to the Lagrange multiplier, and then lambda and C go to 0. So in the non-abelian theory, C would not go to 0, it would go to a bracket of C with C. So it's ultimately where C goes is somehow the Lie algebra of gauge transformations. So so I'm being kind of a little bit quick with that story. So yeah, so there is some kind of interesting structures of homological algebra going on here. But there is this operator on the space of fields, and from the standpoint of this, and this operator squares to 0. And in terms of that operator, my Faddeev-Popov action looks like the original classical action integral of BdA plus Q of something. And this something is the integral over the surface of little b d star a. So, so Faddeev-Popov action is the shift of the original action, original BF action by something Q exact. So, okay, and let me maybe denote this kind of, so it's Q of something. Please, there's a question.
Yeah, so Q is nilpotent, right? Q squared is
Yes,
0.
absolutely. Absolutely. Q squares to 0. That's indeed. So, and we can see it here, for instance, A goes to DC and then I apply Q again, C goes to 0, right? So DC also goes to 0. So if I apply Q twice to A, I get 0. Or if I apply Q twice to B, for instance, B goes to lambda and lambda goes to 0. So, so Q squares to 0. In this example, very easy to see. So,
So do
let
you
me,
have any expression of Q in terms of this field, A, B, C?
sorry, could you say again, please?
So do you have any closed form expression of Q in terms of the field?
Yes, absolutely.
B.
I just gave it to you, the expression. So, well, I mean, you can write it in some other notations. You could write it as like DC variational derivative in A plus lambda times variational derivative in B.
I see. Thank you.
Yes, but essentially these formulas that I wrote are the formula for Q, right? So they define Q completely. So if I also tell you that Q acts by derivation as a derivation on functions on fields, so I told you how to act on linear functions on fields. And then if you have a polynomial function, then you just use the Leibniz rule. So Q is defined completely by these formulas. So okay, so now let me call this expression in brackets. Let me call it psi. So psi also sometimes is called the gauge fixing fermion. So something that's important is that the only place where the metric appears in S is, okay, S0 did not depend on the metric, right? So S0 was just integral of BdA. Q does not depend on the metric. The only place where the metric appears is in this star here. That's the only place. Let me write star sub G, so it depends on the metric. That's the only place where the metric dependence occurs. So this will be important for us in a second. Now, let me maybe also write down the equations of motion for this new action, the S, the Faddeev-Popov or BRST action. So equations of motion for S. So they are the following, so that A is 0. So these are just the equations of the critical point. Now, d star of A is also 0. That's from taking the, so you extract the equations of motion from taking derivatives with respect to various fields, right? So I take the derivative with respect to B, I get that dA is 0. I take the derivative with respect to lambda, I get that d star of A equals 0. So I take the derivative with respect to A, I get a little bit more complicated equation, which is dB minus star d lambda is 0. And then also I can take a derivative with respect to C and with respect to B, and that gives me equations that the Laplacian of B and the Laplacian of C are both 0. So, okay. Now, well, any questions so far? So maybe if you haven't seen BRST or Fadeev-Popov constructions, then maybe this is kind of a little bit new, but I tried to at least explain what these constructions are about. So Fadeev-Popov construction is about trying to make sense the path integral over the quotient. So it's resolving the path integral over a quotient, and BRST construction essentially it is ultimately the same. So it just sort of tells you that you have this new action that you can, which in this example coincides with Fadeev-Popov action, that you can integrate over this extended space of fields, and this is the correct path integral. It computes the same as the path integral over the quotient. So it gives the same quantum theory. And ultimately, you can sort of choose whatever you want for this expression in brackets, and it will always give you the same quantum answers. So that's the idea of the RST approach.
So this Q
Mhm.
acting on this object that you are calling as
Yes.
a fermion, because it has a Grassmann parity -1, right?
Exactly.
Odd Grassmann
Yes, yes.
in the presence of this B field, right?
Absolutely. Yes. Mhm. Yes. So Q is an object of Grassmann degree, as you say, or ghost number +1. And B has degree -1 and A has degree 0. So yeah, psi has degree -1. So Q acting on psi is something of ghost number 0. So, indeed. So yes. Now, now let's do the following strange procedure. So let's change somehow change do a change of variables, a change of coordinates on the space of fields. So let's talk about the redefinition of the space of fields, or new coordinates on the space of fields, new parameterization. So I want to split my one form A as a, let me sort of denote it like fat little a plus fat little a bar. So A was a 1 form, so I want to split it as a 1,0 form plus a 0,1 form with respect to a complex structure. Let me be even more sort of down to earth, and let me, although I don't completely have to do it at this point yet, but let me specialize sigma to be the complex plane with standard complex coordinates. So then I'm just writing my one form A, capital A, as little a times dz plus little a bar times dz bar. So z and z bar are standard complex coordinates. So yeah, and then my notations, little a bar are kind of scalars. So they're scalar fields now. And fat objects, they are one form valid fields. So, and then, okay, so we have split our 1 form into 1,0 form and 0,1 forms. And now I also want to introduce certain complex combinations of the field capital B and the Lagrange multiplier, which seems completely ad hoc, but you will see why I'm doing it in a moment. So let me introduce this new field, call it gamma. So lambda plus IB over 2. And similarly, I have its complex conjugate gamma bar. So I have now two complex scalars, gamma and gamma bar. So I have created real fields B and the Lagrange multiplier for two new complex scalars. Okay, so then I can talk about the theory in terms of this new parameterization of fields A bar, gamma, gamma bar, and then the ghosts B and C. So, and yeah, A and A bar so came from A, and gamma, gamma bar came from B and lambda. So, okay, then it turns out that the action that I wrote before can be written well up to some. I'll generally be kind of sloppy with some normalizations and signs, but for the moment, let me write it. So so the action will be the following. So del bar here is the Dolbeau operator, so it's a partial derivative in z bar times dz bar. Plus gamma bar del A bar plus B del bar C. Okay, so this fat del bar was the Dolbeau operator, Dolbeau differential. And okay, so another way to write it, just using somehow this coefficient fields, little a bar, so is as an integral over the plane with respect to the standard area form, gamma del bar A plus A bar del gamma bar plus B del bar C. And here del bar is just the derivative in z bar. And likewise del is the derivative in z. So yeah, and then here you might recognize some standard CFTs, right? So first of all, let's notice that this action written here is manifestly conformally invariant. Why so? Well, because the only geometric structure that is used here is the complex structure. So we don't use the metric. We only use on the surface. We only use the complex structure, and it enters through through the differentials del and del bar, and of course through the notion of 0, 1, and 1, 0 forms. So another way to see that the theory is conformally invariant was actually, we could see it a long time ago when we were writing down the full action. So the point is that the dependence on the metric is through the star here, or the star appearing here. However, what is conformal invariance classically? It means that if I rescale the metric by transformation, then the action wouldn't change. But when I rescale g to omega times g for g some wave factor, then star acting on some p form would rescale by omega to the power, well, the dimension of the manifold over 2, which is 2 over 2 minus p, which is, since we are acting on a 1 form, it doesn't rescale at all. It just scales by the factor omega to the power 0. So, so star of a middle degree form is a conformally invariant object. Doesn't change with Weyl transformations of the metric. So that's why this is a conformally invariant theory. Right? Because star acts on a middle degree form, which is degree 1 for a two-dimensional manifold. So okay, so that's another explanation of why we got a conformally invariant theory. Another point is that here you can see that, well, our 6 fields, A bar, gamma, gamma bar, B, and C, so they kind of got grouped into 3 kind of pieces of the theory. pieces of the action, so they don't somehow interact they only interact in pairs, A with gamma, A bar with gamma bar, and B with C. And essentially what you have here is a sum of 3 non-interacting theories. And this theory is essentially what's called beta gamma or BC system in the standard terminology, but with particular choice of conformal weights of fields. This is its this is the holomorphic one, this is the anti-holomorphic one. And this is, well, it is essentially, well, how to say this, complex scalar field, but sort of odd scalar field. So these are 3 kind of well-known.
But usually beta gamma system has odd Grassmann parity, but here gamma and A are even Grassmann parity, right?
Yes, no, you're right. You're right. So usual beta gamma system also has fermions. So has spin 1/2
but
octaves.
BC system, BC system is fermion. Beta gamma system are boson. Right.
Right. So what is important for me here is that the kind of the kinetic operator in the action for the beta gamma or BC system is the Dolbeault operator, and this is the kinetic operator here. And
the last term is the Grassmann parity is there. Grassmann parity is odd.
Yes, this is odd, and this is even. I was just trying to make connection to some standard examples of CFTs. But yeah, so here these are odd scalars. Actually, all fields are scalars here. No, sorry. Gamma and gamma bar are scalars, BC are odd scalars, A and A bar are kind of 1, 0, and 0, 1 forms respectively. Okay, but so these are this looks like 3 kind of non-interacting field theories, but they do talk to each other, but in a subtle way, not in the action. They talk to each other through this operator Q. So if I write the operator Q in these new variables, then it sends A to minus del C, A bar to minus del bar C, and B to gamma plus gamma bar, and the other fields are mapped to 0. So somehow this 3 theories, they do talk to each other, but through Q. So Q kind of mixes them. Now, the equations of motion of the new theory, so in the new variables, is that A is holomorphic, gamma is holomorphic, A bar is anti-holomorphic, gamma bar is anti-holomorphic, B is harmonic, so del bar is proportional to the Laplacian, C is C is harmonic. So these are the equations of motion. Now, the BRST symmetry. So I'm moving at approximately 1/3 of the speed that I was expecting, but which is kind of probably the correct. It always works like that. So, yeah, I think yeah, maybe I will not come to non-abelian theory, but we'll see. We'll see. So BRST symmetry. So we can think of this Q as sort of defining the kind of it's like a continuous symmetry on the space of fields, but parameterized by the odd line rather than the real line. And we can apply Notre's theorem to it, to this symmetry. Sorry, Notre theorem, Notre theorem. So Notre's theorem, well, allows you to extract a conserved current out of continuous symmetries. So you get a current, which in this case means that it's one form dependent on fields. Let me call it J total. And this current is, well, up to some normalizations, it's dz times gamma del C, and also has an anti-holomorphic part, dz bar, gamma bar, del bar C. And let me call this holomorphic and anti-holomorphic components. Let me call them J and J bar. So this current is conserved. And this is what Notre theorem gives you. It gives you currents that are conserved. So conserved means that there are differential. So this is a one form on our surface, but dependent on fields. So somehow tensor functions on fields, if you like. There's a more precise way to say it, but yeah. So it's a one form dependent on fields. So, and it is conserved in the sense that if I apply the de Rham derivative to it, then I will get 0 if the field satisfies equations of motion. So I get 0 modular equations of motion. That's what conserved means. But in fact, there's kind of an even more, and this is something that you can check using the equations of motion above. But in fact, there's a more, there's a stronger property here, stronger conservation law, which tells you that actually separately the holomorphic and anti-holomorphic parts are conserved separately. This is not automatic, but it is true here. So modular equations of motion, separately the holomorphic and anti-holomorphic parts are conserved as well. So this is a stronger statement. Now, okay, so that is kind of one interesting object that we can extract from the fact that this is a BRST theory. So we can extract this current J tot, conserved current. Another conserved quantity that you always have in a field theory is the stress energy tensor. And probably the key player in a CFT is the stress energy tensor. So, and well, let me use the kind of Hilbert's definition of the stress energy tensor that, well, let's say I write its components with respect to some coordinates. So, but what it is, it's the, up to maybe some normalizations, it's the variational derivative of the action with respect to metric. So let me write SG explicit. So write a G subscript explicitly to indicate that S depends on the metric in some way. And I need to take the variational derivative with respect to the metric, or maybe rather inverse metric. And well, if I'm careful with, maybe there's some normalization factors like square root of the determinant of the metric, something like that. So in other words, I should consider the variation of the metric and how S changes under a small change of metric, and it would change like, so the variation of S would be something like that. So the variation of the metric, of the inverse metric, times T. So that's kind of the Hilbert's definition of the stress energy tensor through the variation of the action with respect to metric. Now, okay. So now one can try to calculate what it is in our example. So, and then it's important what I told you a few minutes ago, that the way that S depends on the metric is just through the dependence of this star here. And Q itself does not depend on the metric, and then S0 does not depend on the metric. So if I take a variational derivative with respect to the metric, then I will get, well, okay, this will drop out, it does not depend on metric. I will get Q of the variational derivative of this object in metric. So the stress energy tensor will be Q of, well, of the, let me omit this, suppress this square root of the determinant of the metric factor. So it will be a variation with respect to G of the gauge fixing Fermi. Well, let me again put subscript G because it depends on the metric. So, and let me denote this new object by capital G mu nu. So what we got is that the stress energy tensor is automatically Q exact. So it's Q of some object, G mu nu, which one can calculate. So it's a little computation. Let me just tell you the result. So you just essentially need to know how the Hodge star changes when you change the metric a little bit. So the computation tells you that this the tensor defined by this G mu nu. So if I kind of write it covariantly, so write it write the kind of the full tensor. This is the following. It has dz squared component, which is a del b times dz squared. It has a dz bar squared component, and it has no zz bar component. So let's write it 0 times dz bar. And okay, so let me call this z component, let me call it g, and z bar component, let me call it g bar. Okay, so all right. And then I can calculate the stress energy tensor as just Q of G. And again, it's a small computation, which gives me the following: dz squared times del B del C plus A del gamma plus dz bar squared del bar B del bar C plus A bar del bar gamma bar. And that's it, plus 0 times dz bar. So the coefficient of dz squared is, well, the zz component of the stress energy tensor, which one commonly denotes capital T in the CFT notations. This is z bar component, which one commonly denotes T bar. And 0 is, of course, the z bar component. And the fact that it is 0 is exactly the statement of conformal invariance, because what T z bar measures, it measures the reaction of the action to a small Weyl transformation, right? And so invariance with respect to Weyl transformations of a metric is exactly the vanishing of T z bar. And well, TZZ and TZ bar, they measure kind of reactions to different transformations of metric, namely those that change a little bit the induced conformal structure or complex structure, right? And this reaction is non-trivial and is measured by this stress energy tensor. But, well, in the example at hand, it's non-trivial, but it is Q exact. So we have calculated the stress energy tensor. And we figured that, well, it's Q exact. So, and this is true also component wise. And we have the conservation laws. So we have that G is holomorphic modular equations of motion, and T is holomorphic modular equations of motion, and likewise for the G bar and T bar. Okay, so this is actually what I wanted to say about classical theory, and kind of now I wanted to talk about quantum theory. So, you know, maybe it's a good time to make, we should make a 10 minutes break. Maybe we should make. All right, let's continue. So then I explained the kind of the classical part of the story for abelian BF theory, and now I want to go to quantization. So moreover, I want to consider path integral quantization. One can choose different languages, so one can do canonical quantization on a cylinder mapped to a punctured plane or whatnot, but I want to use, and different languages would give you the same result, but let me use the path integral language. So, so what we are interested in is correlators. We are interested in correlators. of the following sort. So we want to take some fields, phi1, to put it at the point z1, phi2 at the point z2, and so on, phi(n) at zn. So by the way, I want to fix my surface to be C. So I want to be on the complex plane. So on the plane, I have marked several disjoint distinct points, z1, z2, and so on, zn. And I want to put fields at different points. So what do I mean by fields here? I mean composite fields. Composite fields. And what do I mean by composite fields? I mean polynomials in sort of fundamental fields in terms of which the action was written. Polynomials in those and their derivatives, maybe higher derivatives at the given point. So, or what's called differential polynomial. So polynomial in those objects and their derivatives, differential polynomial in the fields A bar, gamma, gamma bar, B, C at those respective points, Z1 and so on, Zn. So, and then, so I want to calculate such correlators. And so I want to understand them as the integral over my space of fields of, well, the exponential of some kind of convenient normalization minus 1/4 pi times the action. And then the product of my fields. So I think that, okay, I have some kind of expressions, functions on the space of fields. And then I'm considering the product of these functions, and I'm averaging them with respect to a measure on the space of fields, kind of a Gaussian measure, because S is a quadratic function. So I'm considering this Gaussian average. And I should normalize by, well, the partition function, which is the integral of exponential of minus S without those fields under the integral. So, okay, so those are kind of infinite dimensional integrals. So there's some discussion of how to define them, but in this case, it's defined by the Week's lemma. So the function S is quadratic, the action is quadratic, so it's a free theory. And this means that, well, let me call star this path integral expression. So the path integral expression is given by Week's lemma. Well, which in this case is not a lemma, it's a definition essentially of. So it's a lemma when you are calculating a finite dimensional, when you have a Gaussian measure on some finite dimensional space and you want to compute moments of this measure. But now we have infinite dimensional Gaussian measure, so here it becomes a definition. So it's given by Week's lemma with certain propagators. And the propagators are the following. So the propagator between A at the point W and gamma at the point Z is 1/W minus Z. And this is the Green's function for the Dolbeau operator, or maybe 1/pi times Dolbeau operator. So the propagator between A bar and gamma bar is 1/W bar minus Z bar. And similarly, this is the Green's function for anti-homomorphic Dolbeau. And we also have the propagator between the two ghosts. So C at W and B at Z. So I say propagator, but you can also understand it as a two-point correlation function in this theory. So so it's 2 times logarithm of the distance. plus a constant, and well, this constant depends on somehow on the infrared regularization of the theory. So constant depending on the infrared regularization of the theory. So what's that about? Well, you're trying to write down the Green's function for well, up to some constant up for the Laplacian. So you're trying to, okay, that's the integral kernel for the inverse of the Laplacian. But to invert the Laplacian, you need to put some boundary condition, some boundary problem for the Laplacian. So you need to put the Laplacian in a large disk of some large radius and put, let's say, Dirichlet boundary condition. So then this C would be something like -2 logarithm of that radius. If you regularize this way. Okay, so now, so then you can start calculating correlators of composite fields using this essentially this definition with as a sum of over Weeks contractions. So let me give you an example. So let me take the field A del gamma at a point. So I will write the point either in brackets or as a subscript, whichever is more convenient. Well, okay, so let me write it in brackets for the moment. So A del gamma at the point Z1, gamma, sorry, A gamma C at a point Z2, at the point Z2, and del bar B at the point Z3. So let's say I want to calculate such a correlator. So there will be different Weeks contractions. So let's say, for instance, I can pair A with gamma here. I can pair gamma with A here and C with B here. So the contraction of this contraction of A with gamma. So that gives me the propagator that I wrote here. So it will be 1 over W minus Z. So this contraction of gamma with A, okay, so it would have been 1 over Z1 minus Z2 because of this, but I also have the derivative hitting it, derivative in Z1. So if I'll calculate that, so let me work modulo signs here. So it's, sorry, it's Z1 minus Z2. So here I would have 1 over Z1 minus Z2 squared. So modulo sign, maybe there's a minus sign. And then I'll also have, okay, so here I have contraction of C with B, which gives me this twice log of the distance, but then I need to hit it with del bar with respect to Z3. So that gives me, well, again, up to signs, 1 over Z2 bar minus Z3 bar. Okay, so this contraction gives me 1 over, well, plus minus, 1 over Z1 minus Z2 cube times Z2 bar minus Z3 bar. Okay, but I can invent some other contractions. For instance, I could contract A with gamma inside here, but then I would run into a problem. So I would have to evaluate this Green's function at, well, W and Z coinciding, and that's a divergent object. So what I want to do here is to write normally ordered fields. And normally ordered fields exactly means that I'm prohibiting self-contractions. So I'm prohibiting self-contraction inside of the field, so it's not allowed. So likewise, here I could imagine contracting A with gamma, but I'm saying, okay, now I want to normally order this field. That means that this contraction is prohibited. And okay, so once I've normally ordered the products appearing here, in the last term, well, normally ordering it doesn't do anything because there's no product involved. So if I normally order all the fields, then I don't have problematic contractions. And actually, then in this example, this would be the only weak pairing. So the only way to pair all the fields with allowed contractions, where these two are not allowed. Yeah, it's the only way to pair all the fields. So this is actually the full answer for this correlator. In some other examples, you could have several terms. So each term corresponding to a perfect matching on the fields involved. So another way to maybe draw this pictorially is the following: that well, if I want to calculate the correlator of several composite fields, and let's say that my composite fields are normally ordered monomials. Differential monomials. So then let's say I have point Z1 where I have something, let's say, I don't know, of some order, let's say cubic in fields. Let's say, I don't know, I have, I don't know, del, let's say my field there is del A times, I don't know, del bar to the power 7 of gamma bar, and then I have C. So I just write this individual derivatives of individual fundamental fields on the prongs coming from this vertex. So I have several points and several composite fields. So maybe another one is, I don't know, of degree 5 in monomial of degree 5 in derivatives of fundamental fields and so on. So I have several points and several differential monomials. So then what is the computation of a correlator? It's a sum over the ways to just connect pairs of these prongs or leaves here by propagators, right? So you just connect all of them. And this is not allowed, right? So I'm not allowed to contract two prongs of the same on the same vertex, and that's the normal logic that I'm not allowed to do that. So yeah, so let's see, can I do it? Yeah, okay, sorry. So let's say I do that, I do this, I do that, and okay, I have too many. Okay, let me just okay, let me cheat a little bit and okay, add a new field here and connect it like that. So computing a correlator is just a sum over pairings, right? A sum over ways to pair this leaves, right? And each such pairing. So for each kind of edge here, I would write the corresponding propagator or its derivative if there were derivatives here. And this will give me some sort of expression in terms of the coordinates of these points. So this was just a simple example. So ultimately, the computation of a correlator, computing correlators of normally ordered monomials just gives me as a sum of such pictures or Feynman graphs. And well, here you see that Feynman graphs are very easy to compute. There's no integration involved. It's just, yeah, Feynman graphs with fixed vertices. Okay, so now maybe one more remark about this composite fields, the objects that I can calculate the correlators of. So, okay, so the space of composite fields all those are, yeah, so differential, let me call it differential, composite fields at a point Z. So these are differential polynomials in fundamental fields. So fundamental fields for me are this A bar, gamma bar, B, and C. Well, I think of them as normally ordered. But then I can also quotient out things which have vanishing correlators with everything else. So for instance, something like del bar gamma, if I put it at some point, and then I put in some other point, some other fields, then it will always be 0. So ultimately, because gamma will talk by a propagator to something, and so there will be 1 over z minus some other position distinct from z, and then I will hit it with a derivative in z bar because of this del bar here, which is 0. So yeah, but it's related to the fact that del bar gamma equals 0 was a classical equation of motion. So here I want to just quotient by things that vanish by classical equations of motion. So in this example, this is so there could be some subtleties here in a quantum theory. There could be quantum corrections to the classical equations of motion, for example. But in this free theory, there are no corrections. So now the result here is this quotient can be easily described. So it's a free graded commutative algebra with certain generators, which I can list, generated by okay, the following objects. So you have A and its holomorphic derivatives. So you can take 0, 1, 2, 3, and so on holomorphic derivatives of A. You can take gamma and take also 0, 1, 2, 3, and so on holomorphic derivatives. So I don't have mixed derivatives of A or gamma because they would automatically vanish modular equations of motion. So I have the field B hit by at least one derivative, and I'll explain why I write it like that. And field C hit by at least one derivative. So these fields, so these are the generators of the part of the set of generators. I will write the other generators in a moment, but these ones are, well, they are holomorphic, so they're killed by that bar. Killed modular equations of motion. You have sort of the anti-holomorphic counterpart. And so these fields are killed by, so this is kind of the anti-holomorphic sector of the theory, so they're killed by del. And there are two fields which are not killed by either del or del bar. These are B and C. They are kind of harmonic, but they're not holomorphic or anti-holomorphic. So this is kind of the holomorphic sector of the theory, and this is the anti-holomorphic sector. And B and C are neither. So I should also mention another important point, and that's that, well, in what we have here is not just a free graded commutative algebra, but there's also a differential. And the differential is given by Q. Q from before, we also will discuss in a moment its quantum meaning, but there is the differential Q. So it endows this algebra with the structure of a differential graded commutative algebra. And one can compute its cohomology. And it is a computation, and this cohomology is very important. So it is what's oftentimes called observables of the theory. So observables are, well, Q closed composite fields, modulo Q exact composite fields. And they can be identified, and this is a computation, with polynomials. So here I need to use kind of this real parameterization of fields. Here it's more convenient. So a real field capital B and the ghost C. So that means I can take polynomials in B or polynomials of B times the ghost C. So these are the observables. Okay. Now,
Sorry, what is capital B? Use different
yes,
from
capital B.
small.
Remember, it was from the original class parameterization of the classical
Oh,
theory. That B. It was
classical
that B.
theory, right?
Yes.
That B, I
So
see.
it can be expressed in terms of gamma and gamma bar. So it's something like gamma minus gamma bar divided by 2i. it's something like that. Okay, so this is something that's that will be important, or might be important depending on whether I will actually have time to talk about the sort of TCFT structure here. But okay, so these are kind of the Q-closed observables of the theory. Okay, now let's now talk about operator product expansions. So, okay, so an operator product expansion is, well, it's an expression of the following type, that if you have two fields, one at a point W and another at a point Z, and you kind of imagine that this point W is very close to the point Z, then you want to be able to replace under the correlator this pair of fields with some sort of linear combination of single fields at one of the 2 points, either Z or W. So you write something like that this product of fields can be replaced with something like a sum where the terms are some singular function of W minus Z, some singular coefficient function, typically some negative power of W minus Z, or could have things like logarithm of W minus Z, but actually that doesn't occur in this particular theory, in the free theory. So singular coefficient functions times some other fields, so some composite fields, quantum fields, and plus some regular parts, regular as W approaches Z. So in this theory, regular really means holomorphic, although more generally it could just mean continuous. So, but what does this expression mean? So, such an expression means that it means that I can make a replacement of the left side with the right side under a correlator. So that means that if I take these two fields, and then also some collection of test fields at some other points. So some test fields, Vn of Zn. So these are some test fields. So then it is so it can be replaced as in the asymptotics W approaching Z with the sum of my my coefficient functions, the correlator of this new field phi twiddle at the point Z with the test fields. So that is what having an OP means. So maybe again, sort of how to think about it. So we are on the complex plane, although we could have been on the surface, on a more general surface. So, and I have points W and Z, and I have my two fields Phi1 and Phi2, and I'm considering the limit of W approaching Z. And I also have a bunch of other points where these test fields are plugged in. So, and then I'm studying this correlator, and I want to express this correlator. Oops, what happened? Yes. Okay, very good. Apologies. So, okay. So where were we? So we want to study such correlators, right? So we want to let field Phi1 approach field Phi2. And we want to say that with an arbitrary collection of test fields, we can make a replacement of this pair of fields with a sort of a linear combination of a single field plugged in at the point Z. So that's what it means to have an OP. So here I'm writing this sort of asymptotic symbol, but actually you can achieve an equality here if you write down explicitly all the regular parts. And in this theory, actually, you can do it in the theory that we are discussing. So, okay. So then it turns out that the OPs, so since we can write down correlators explicitly in terms of Feynman diagrams, you can also extract from it a recipe how to write down OPs. So OPs as an operator product expansion. So an OP is given ultimately by Feynman diagrams with 2 vertices. With 2 vertices where phi1 and phi2 are plugged in, and with also graphs with 2 vertices and with leaves or loose half edges. And the idea is that those leaves are leading to the test fields. So they are kind of chopped edges leading to the test fields. So, for instance, if I were looking at this graph here, so then I could, let's say, I could have had some kind of Feynman diagram. Here, choose some color, some Feynman diagram, like, I don't know. And then maybe, I don't know, something might be going here. And then I'm interested in how, in the asymptotics as W approaches Z. So, so then it turns out that I can just essentially look at the subgraph, at the subgraph of such a Feynman graph, given by, well, just edges connecting these 2 vertices and the leaves leading to the test fields. So that's the idea. So, for example, let's say, okay, let's let's maybe do, well, okay, yeah, let's do the following. Let's do gamma del C at the point W and A del B at the point Z. So then what are the possibilities? So I should imagine that this sits under the correlator with a bunch of test fields. So then I can, here I can entertain sort of partial weak contractions, which is tantamount to saying that I'm looking for graphs with leaves. So one possibility is to contract both C and B and gamma and A. And then sort of the test fields are contracted in some way. So that will give us -1 over W minus Z squared. Sorry, cube, actually, cube. Why so? Because, well, this pairing gives us 1 over W minus Z squared, and this is 1 over W minus Z. So in total, I get 1 over W minus Z cube. So in other graphical conventions, if I think of this sort of little corollas, I have gamma times del C at the point W. I have A times del B at the point Z, and sort of some test fields far away. And then I'm connecting gamma with A, and I'm connecting del C with del B. So this is kind of my subgraph, essentially. And this one doesn't have leaves. Now, another term is when I do the contraction of del C with only del C with del B, and I don't contract gamma and A. So then I get 1 over W minus Z squared, and the uncontracted part is A and gamma. So times A and gamma, and actually, okay, it's gamma at the point W, A at the point Z, and I should normally order it as in I should prohibit doing the contraction between the 2 fields in the correlator, because that contraction is already a part of that term. So this corresponds pictorially to, well, gamma del C, A del B. So I'm contracting A with del B. And gamma and A, they kind of lead to some test fields far away. Now, the third possibility is to do the contraction between gamma and A and not contract del C with del B. So that gives me -1 over W minus Z, normally ordered product of del C at W and del B at Z. So, and that corresponds to, well, in this pictorial notations, I'm contracting A with gamma, and del C and del B lead to the test fields. And also I can sort of not do any contractions at all between the two fields, and sort of all the prongs lead to the test fields, but that will be something that's definitely regular as W approaches D. So, okay. And then, okay, so here there's, it's not still quite in the OPE form because I want to have a field at the point Z, and here gamma is a field at W. So I actually, what I need to do is I need to do the Taylor expansion of W around point Z. So I have, so this is gamma Z plus W minus Z times the derivative of gamma at the point Z plus higher derivatives, plus in principle also things like W bar minus Z bar del bar of gamma at the point Z, but that vanishes by equations of motion. So, and then there will be sort of higher holomorphic derivatives, but they will come with W minus Z squared and so on. So they will be a part of the regular term. So the only part that affects the singular term is this term. And likewise, here I should also expand C at the point Z. So I should replace this as del C at Z plus, well, del squared C at Z times W minus Z plus and so on. But actually this already goes into the regular term because it's times 1 over W minus Z goes to regular term. So the singular term is just 1 over W minus Z cube minus gamma Z, well, gamma times A at the point Z over W minus Z squared. Sorry, that was a plus. Minus, that was a minus here. Minus, let's see. Okay, so let me write it like that. Plus 1 over W minus Z. Normally ordered expression del gamma A times plus del B. That's everything at the point Z, plus the regular part. So yeah, so this is ultimately how you calculate OPs. So they are, so you are looking at Feynman graphs with two vertices and with leaves allowed, and then you also need to re-expand the fields that you get at W in terms of the point Z using just Taylor expansion. So that's the recipe. And in our example, we got this sort of nice Laurent polynomial. So Laurent series where we wrote explicitly that its principal part. So, but you can, if you sort of work a little bit more, you can write explicitly the regular part as well, if you just don't forget the regular terms. Maybe another example where let's work out the regular part. So let's just do the simpler example. Let's take the fields gamma at the point W and field A at the point Z. So let's write down this operator product expansion. So here, well, we have our two fields and gamma at W and A at Z. And we can either connect them by an edge or not. And then kind of the both half edges would lead to the test fields. So when we connect them by an edge, this gives us 1 over W minus Z. And if we don't connect them by an edge, then we get gamma at W, A at Z normally ordered. But then you can express this in terms of the point Z, just expanding gamma by Taylor expansion. So that gives us, well, okay, sum over K and L non-negative, 1 over K factorial, L factorial, the appropriate derivative of gamma at the point Z times A at the point Z. times W minus Z to the K, W bar minus Z bar to the L. But here actually many terms are zero, modular equations of motion, and hence zero under any correlator. So the only terms that are non-zero is when L vanishes. So it's actually, as well, as a quantum field, it's the same as 1 over W minus Z plus, well, gamma A at the point Z plus W minus Z then gamma times A at the point Z plus W minus Z squared times normally ordered then squared gamma times A and so on. So here I'm just illustrating that you can write down explicitly this regular part, no problem. So now having this technology, we can start doing various computations. For instance, we can calculate the OPE of the stress energy tensor with itself, for example. This is a little bit annoying because, well, both of them, so it's not a monomial, it's a sum of two monomials. So there will be several terms to consider, but it's a little bit of a computation, but it leads to the following. It's okay, 2t at the point Z over W minus Z squared plus the derivative of t at Z over W minus plus the regular part. So, okay, what does it mean? Well, here we recognize the standard OP between the stress energy tensor with itself, but moreover, there is no quartic pole here, right? So in a general OP, there would be C over 2 divided by W minus Z to the fourth, right? Something like that times the kind of identity field. But, well, there's no such term here. Instead of C, there's 0. So that means that the central charge is 0. Now, we can also do some other examples. So, for instance, what were other important players in the game? There was the field J, which was the which was this BRST Notre current associated to BRST symmetry, which was, what was it? It was gamma del C. So that was from the previous hour. And we can consider, for instance, its OP with the field G. Well, of course, everything is normally ordered. So in the field G was this Q primitive for the stress energy tensor that was A del B. And actually, this is exactly the OP that we were considering here. That's exactly the one that we just calculated. So that gives us this cubic sort of pole, minus 1 over W minus Z cube plus gamma A at the point Z. And that's the quadratic pole plus, well, the last term is actually the stress energy tensor plus the stress energy tensor at the point Z of W minus Z plus regular part. What else? We'll have that TGOP will give us a 2G over W minus Z squared plus del G at the point Z over W minus Z. Let me stop writing plus regular. There is plus regular. And TJ will be twice J. That's the quadratic pole plus the derivative of J. That's the first order pole. So, okay, so what do these things mean, for example? Well, it means that that G and J are primary fields. Actually, I made a mistake. There's no 2 here. That these two OPs mean that G and J are primary fields. So you test fields for being primary by looking at their OP with the stress energy tensor. Means that G is primary of conformal weight 2. So there's this coefficient here. And the last one tells us that J is primary of conformal weight 1. So that's the coefficient 1 here. So also you can calculate the OP of G with itself, and this is just regular, and also of J with itself, and it's also just regular. But also you can start taking various fields and test them for being primary and figure out the conformal weight by taking the OPE with those fields. And then, for instance, the original fundamental fields. So actually, I wrote this little table answering a question in the end of the last hour. So you have this. So the conformal weights for the original fundamental fields are somehow just this. So, and here you have the holomorphic and anti-holomorphic conformal weight. So for instance, for A, it's 1 and 0, for a bar 0 and 1, and all the others have just conformal weights, both conformal weights equal to 0. So, okay. Now, also, now that we know how to calculate OPs, we can also calculate other usual structure of CFT. We can calculate the Virasoro algebra action on the fields. So you have a Virasoro action or Virasoro representation of the Virasoro Lie algebra on the space of fields at a point. So, well, how do you compute it? So you take, so what is Ln acting on the field phi at a point z? Well, what you should do is you should take E, plug it at the point z, and then take the stress energy tensor and plug it at a nearby point w, and then integrate it against a factor w minus z to the power n plus 1. And you should integrate in w over a little circle. A little circle, so you're integrating over w, so w is kind of going around z once counterclockwise, and I think you should maybe put a 1 over 2 pi I factor. And you can replace in this expression this product of fields with the OP. So knowing the OP, you figure out the what's the action of the Virasoro generators. In other words, just by the residue theorem, so this is the coefficient of 1 over w minus z to the power n plus 2. So n here is any integer in the OPE between the stress energy tensor and phi, right? So you just look at this OP, and depending on which n you are interested in, you might be looking either at singular part of the OP if n is let's see, if n is greater or equal than -1, then you're looking at the singular part of the OP. If n is smaller or equal than -2, then you need the regular part of the OP. But in any case, we know how to write the regular part of the OP as well. So we can figure out the Virasoro representation. There are also the mode operators for the field G. So apart from the stress energy tensor, I also have my field G, and I have kind of a similar, let me call this contour gamma Z. So I have a similar contour integral, but involving the field G instead of the stress energy tensor. And that gives me some other kind of operators on the space of fields at a point. And also I have sort of a quantum definition of what it means of the BRST symmetry, of the BRST operator. So the quantum definition is as follows. So I should take the contour integral over the same contour, j at w, phi at z, and here I'm not writing any kind of power prefactor, so it's just this. So essentially, I'm looking at the first order pole in the OP between j and phi. So this is the quantum definition of the BRST operator. It actually coincides with the classical expectation in this theory. So in total, we have our the action of our Virasoro generators, and also of this G generators. We also have the the kind of Virasoro bar generators that are defined similarly. So, but sort of complex conjugating everything, and the GN bar. And we also have our BRST operator Q. So all of this together is a certain DGLA, differential graded Lie algebra, and acting on the space of composite fields at a point. And a very important property, so there are certain relations here, in particular there are Soror relations between LNs, so Q squares to 0, or anti-commute with itself if you like. But very importantly, you have also the relation that Ln is the anti-commutator of Q with Gn. So Virasoro generators are Q exact in this point, in this theory. And that's a property of TCFT, so topological conformal field theory. So generally, a topological conformal field theory is a theory where the stress energy tensor is Q exact, and G is the common standard notation for the primitive, so for holomorphic and anti-holomorphic parts. So TCFT is just this structure. For the Virasoro action, for instance, it implies that Virasoro generators are Q exact. So, okay, now I'll need to think how to, so I covered a bit less than half than what I was planning to, and then I need to think how to, what else can I say in the remaining time? So, okay, so maybe I should mention, yes, okay. Let's see. Maybe let me quickly mention Witten's descent equations. So, okay, so there are some objects that are particularly important. So, for instance, in usual conformal field theory, L0, L0 bar are important because they sort of eigenvalues, so they act usually diagonally. Their action on fields can be diagonalized, and their eigenvalues are what we call conformal weights, right? Conformal weights are the eigenvalues of L0 and L0 bar. So these are kind of the scaling operators. So L-1 and L-1 bar are also important operators, and they kind of correspond to infinitesimal translations. So they actually act as del and del bar on fields. So if you wish, infinitesimal holomorphic and anti-holomorphic translations. In a topological field theory, the corresponding sort of Fourier components of G fields are, or mode operators for the G field are important. Well, I'll hopefully mention something about why they are important. So, okay, now something that one can study in a TCFT is Witten's descent equations. Okay, now, sorry, I need to sort of strategize a little bit. No, okay, so one can study Witten's descent equations. And this is the following sequence of equations. So it's a sequence of equations on P form-valued observables. So here OP at a point Z is, well, it's a composite field, but valued in the fiber of the bundle of P forms. Let's see, so it's a P form-valued object, P form-valued composite field. So one can study this equation in different theories which have BRST differential, but here let's study it in our theory. So P goes up from 0 up to the dimension of the manifold. So let's call this equation star. And so one is interested in constructing kind of such hierarchies of observables. So 0 observable, 1 observable, or 1 form-valued observable, 2 form-valued observable, linked by this equation. So this equation in particular means that Q should be an observable in the usual sense. It should be annihilated by Q. It should be Q closed. But for O1, it tells you that Q of O1 is D of O0. In particular, it means that if I take O1 and integrate it over one cycle, that should be a Q-closed object in its own right. And likewise, I can integrate a two-form observable O2 over some two cycle. So for instance, over the entire surface, if it's a closed surface, and that's also a Q-closed object. So having Q-closed objects, so it's interesting to calculate correlations of such objects and such Q-closed observables. So correlators of several such objects, so integrals of OP over a P cycle of several such objects are topological correlators. So topological here means that they are independent under small deformations of cycles. So I can move the cycle a little bit as long as I don't intersect the other cycle in which another observable lives, the value of the correlator will not change. So now when this equation star can be solved explicitly, using something called a chain homotopy, or let me call it a descent operator here. So let me call it a descent operator. So it's the following operator: minus dz times the minus first z Fourier mode of g, minus dz bar g bar minus 1. So then it has the property that, so it's a certain operator that acts on form-valued fields at a point. And it has a property that anti-commutator of Q with gamma is the de Rham operator. So then if I start with some O0, some zero observable, such that it's closed under Q, then I can construct O1, I can define it as gamma applied to O0. And then I can construct O2 as half gamma applied twice to O0. This will be a kind of a two observable. Then this sequence satisfies the descent equation. That's an easy check. So, and let me call the sum of these objects, so 0, O1, and O2 satisfying the descent equation. Let me call this a total descendant of O0. So it's an inhomogeneous form-valued object. So, and then one can calculate in our theory how it's, so it's actually always a solution in a TCFT, but we have an explicit formula for G, so we can calculate, calculating OP is how it acts, and it leads to a formula. So I take O0 to be a genetic observable, and zero observable, and for us this was a polynomial of the fields capital B and little c. And then it turns out that this inhomogeneous form, the total descendant, is the following. I should apply that function to, I should replace B by B minus star D, the little b ghost. And I should replace C with C plus capital A, which is a sort of weird formula, but it is how this total descendant works. And it follows from explicit computations, in particular this descent operator sends the ghost to A and sends the capital B field to minus star DB. So here I want to make a side remark. So these two objects appearing here, so they are in their own right non-homogeneous form-valued fields, and they are what's called superfields in some language. So I'm replacing fields B and C by so-called superfields, or more precisely AKSZ superfields, or gauge fixed AKSZ superfields. But that's linking to another construction of topological field theories that I don't have time to talk about, sadly. So, okay, now so we can play with this Witten's descent. So for instance, I promised you topological correlator. So here's an example of a topological correlator. So let me take the field C, the ghost, which is a zero observable. Let me descend it once. So I can descend up to twice, right? So here's the second descent, this is the first descendant. So let me descend it once. So take it at a point W, but it's a one form in that point W, so I should better integrate it over a one cycle. So one cycle, so W will go in a one cycle. And I also take another zero observable at a point Z. So then such a correlator. So, okay, so I have a point B. Sorry, I have a field B at the point Z. And I also have some one cycle for the point W, which I wanted not to intersect the point Z, not to pass through the point Z. So then such a correlator is actually equal to 4 pi times the winding number. So in particular, it's 4 pi times an integer, and it doesn't change if I deform the contour as long as I don't pass through the point Z. So this is the simplest example of such a topological correlator. So another kind of application of the Witten's descent is that on the zero observables, I think I denoted at all the space of zero observables, one gets the structure of so-called BV algebra. And that's kind of, it's constructed in terms of descent. So you have the pointwise product on this BV algebra, which is just putting the two fields at the same point. You have the Poisson bracket of degree -1, of ghost number -1, which is defined like as follows. So I take two zero observables, I descend one of them once, put it at a point W, I don't descend the second one, and then I integrate in W over a little circle around Z. So that gives you a Poisson bracket. And then you have the so-called BV operator, which is given by G0 minus G0 bar up to some factor, 1/2i. And it's also called in some notations G0 minus. So, and this is a second order differential operator with respect to this product. And well, there are kind of certain relations in this algebra, so it's some sort of enhancement of this Poisson algebra. And sort of every topological conformal field theory has such a BV algebra structure, but in the example of abelian BF, you can calculate it explicitly. And so, for instance, this BV operator becomes just the second derivative in the field B and the field C in this example. And the Poisson bracket is also just the Poisson bracket generated by the pairing of B and C. So it's like that. Okay, so so let me maybe then, so I'm kind of out of time. So let me say just a few things maybe in words. So one can use Witten's descent to study deformations of CFTs or of TCFTs. So, and there's one can study deformations of the following type. So you pick some zero observable in your theory, and you change the action of your theory by adding to it the integral of over your surface of the second descent of your zero observable, maybe times some coupling constant. So it turns out that for this to be a consistent deformation of a TCFT, so you also need to simultaneously change somehow the BRST operator and G field. So for this to be a consistent deformation, O0 has to be an observable satisfying the properties that its Poisson bracket with itself must vanish, and that the Laplacian of this observable, this BV Laplacian, must also vanish. So then it is kind of a consistent deformation. And then you can play with different zero observables in abelian BF theory. And then you can take your abelian BF theory, the one that we just discussed, consider its kind of n-component version. So that means that I can take n copies of non-interacting abelian BF theories. And then I can turn on a certain zero observable, which looks like that. So it's a cubic observable, where this is, well, some tensor, coefficients of some tensor. And then it turns out that this observable will be will satisfy these properties. So will give rise to a consistent deformation of the theory exactly when this tensor satisfies, well, corresponds to a structure tensor of a Lie algebra on Rn. So when these are the structure constants of a Lie algebra, moreover, this equation tells you that you want a unimodular Lie algebra. So then you have a kind of a consistent deformation of a TCFT, and that is the deformation of abelian BF theory to non-abelian. So, and then you can study this non-abelian BF theory, and our second paper that with Andrei Losov and Donald Humans is exactly about this non-abelian BF theory. And things are harder to study there. Essentially, well, you can calculate correlators, but essentially the correlators are given by, again, by Feynman graphs, but they will have several fixed vertices where your observables are plugged in, or where your fields are plugged in. But they also will have several moving vertices which need to be integrated out, and those correspond to, well, several copies of O2. So when you calculate the path integral, you have exponential of this expression. So so this is no longer a free theory. So you have the exponential of the integral of O2, so you expand it in Taylor series. So you take several of these O2s and you calculate their correlator in the free theory with your observables. So that gives rise to some kind of contractions. So these moving vertices, they are trivalent in this example. So, and then these positions of this hollow vertices, the moving vertices, they need to be integrated out. So each correlation is actually given by some integral over a Cartesian product of several copies of the complex plane. Such integrals are non-trivial to compute. They give rise to logarithms, dilogarithms, polylogarithms. So typical answers for correlators look like polylogarithms. Yes, so and also you can calculate OPEs, but they also contain logarithms. So it's a more complicated theory, but still things can be to an extent calculated explicitly as long as you can compute the integrals involved. Still it is still a TCFT. So it still satisfies the properties of a TCFT. So you still have a stress energy tensor, which is Q exact. You also have some non-trivial anomalous dimensions for some fields in this theory. So this theory is more interesting, more complicated. So you can construct certain kind of vertex operators. And so let's see. So where should I? What else should I say about this? Yes, maybe one somewhat bizarre point. So one thing that fails, kind of structural thing that fails in non-abelian theory is the following. In abelian theory, it can be recognized as a twisted supersymmetric theory, twisted 2,2 supersymmetric theory, conformal field theory. So, and the fact is that this J and G, so you can sort of perform a manipulation theory, manipulation called untwisting in this case, which is a change of a stress energy tensor by an exact term. And this changes the theory in a very subtle way. So the only thing it changes is that it changes the conformal weights of fields. So in this untwisted theory, which is superconformal, J and G, they attain conformal weights 3/2, both. Instead of having conformal weight 1 and 2, they attain conformal weights 3/2. So then you have this two pairs of somehow supercharges, J and G, J bar and G bar. So that gives you the structure of a superconformal field theory. And in the non-abelian theory, somehow that doesn't work. So, and why that doesn't work? Ultimately, because some, so you like your CFTs to be split into non-interacting, or somehow you want them to split into holomorphic and anti-holomorphic sectors. And some things do split in the non-abelian theory and some things don't. So in particular, so J is a sum of, 1-0 form and the 0-1 form, but they are not separately conserved. So that's the one thing that fails. And so the non-abelian theory is not a twisted supersymmetric theory, not a twisted, at least not this sort of theory with a lot of supersymmetry. But that is what it is. But it's still a topological conformal field theory with sort of lots of interesting phenomena. So I sort of said some of the things that I planned to say, but essentially maybe the big point of this discussion is that these are examples of CFTs with where a lot of things can be computed explicitly. So it's just sort of a playground for various constructions of CFT and TCFT. Maybe let me just mention one more thing for which I did not have time to explain, and that is that there is this picture of TCFTs, which is that a TCFT is an algebra over something called framed little disk operad. So a TCFT assigns some answers to configurations of little disks inside a unit disk, and you mark a standard point on the outer disk and some points on the inner disks. And you can sort of calculate this structure explicitly in these examples, essentially by calculating Feynman diagrams. So and how you should imagine. So you should just put a field for each of these little circles and read off some kind of field associated to the outer circle, and the result will depend on positions of the inner disks, radii, and rotation angles. But the way to ultimately compute it is it's some sort of a multi-operator product expansion where you put several fields at the centers of these disks, and you look at the kind of corresponding Feynman diagrams, and sorry, they can have leaves, and you re-expand the result in terms of the center of the outer disk. So you can construct explicitly this TCFT as an algebra over the framed little disk operand. But this is sort of a mathematical way of expressing that you have sort of this consistent structure of multi-OPs. And it also links immediately to the language of Siegel's axioms for conformal field theory, because you can think of these pictures, these configurations of disks inside a big disk, you can think of them as cobordisms. So as cobordisms between sort of surfaces which connect these little circles with the outer circle. So you can think of removing several small disks from a big disk, and this gives you a cobordism. So what you're calculating is sort of a partition function of a TCFT in the sense of Siegel. So I'm sorry, so I just wanted to mention various things that I planned to say, and let me stop here, and sorry for being way over time. Thank you very much.